In this lesson, we're going to talk about particle motion, and especially we are going to talk about how to use derivatives to solve problems that involve position, speed, velocity, and acceleration. Be sure that you have your paper set up in Cornell Note format and pause the video anytime you need more time to write. Okay, so let's do a little flashcard review. Position, remember, is given by S of t. Velocity is the rate of change of your position with respect to time. So since it's a rate of change, that means it's derivative of position with respect to time. So s prime of t. The acceleration is the rate of change of velocity with respect to time. That means that acceleration is the derivative of velocity and the second derivative of position. Speed is denoted as the absolute value of velocity. So speed does not take into account positives or negatives. Okay, another vocabulary term you will need to know is displacement. And your displacement is the distance between your starting point and your ending point. So wherever I started from to where I stopped, the distance between those two things. Okay, so let's talk a little bit about displacement versus total distance. So let's say I'm at my house in Odessa and I want to go to Target in Midland. And so I'm driving down 191, I leave from my house and I go to Midland. If I go straight there, then I am a distance of 25 miles from my house. Okay, so the displacement would be 25 because I am 25 miles from where I started. Okay. However, let's say that I take off for Midland and I get to the airport and I realize that I forgot my wallet. So I have to turn around and go back to the house, get my wallet, and then go to Midland. Okay, in this case, my total distance would not be 25 miles. I am still 25 miles from where I started, but my total distance is 10 miles that I went to the airport, plus the 10 miles I had to drive back home, plus the 25 miles then to get to Midland. So my total distance would be 45 miles rather than the 25. So displacement doesn't care how much you had to backtrack in between, it's just how far are you from where you started. But total distance means every distance I had to drive. Okay, so let's look at the example that's given. The position of a particle that is moving in a straight line is given by our position equation, s equals t cubed minus 6t squared plus 9t. And they've given us units. The time is measured in seconds, and the position or the distance is measured in meters. First question, find the velocity at time t. And remember that velocity is the derivative of position. So what we're going to do is take the derivative of our equation. So the derivative of t cubed is 3t squared. The derivative of negative 6t squared would be minus 12t. And the derivative of 9t would just be a 9. So that's our velocity at time t. That's the formula. Okay, so now what is the velocity after 2 seconds and the velocity after 4 seconds? To answer that question, we're just going to take our numbers and we're going to plug them into our formula. So 3 times 2 squared minus 12 times 2 plus 9 would give me a velocity of negative 3 meters per second. Because remember, the velocity is the rate of change of distance with respect to time. That's why meters per second. Okay. For velocity at time 4, you're going to do something similar. Pause the video and try it on your own first, and then you can check yourself. So the velocity at time 4, I'm going to plug in my 4 into my velocity equation. So 3 times 4 squared minus 12 times 4 plus 9 would give you a velocity of positive 9 meters per second. Okay, now the next question, we are asked, when is the particle at rest? A particle is at rest when your velocity is equal to 0. So we need to set velocity equal to 0 to figure out when our particle stops moving. Okay, so our velocity equation was 3t squared minus 12t plus 9. I'm going to set that equal to 0. I've got to factor this to solve for t because it's a quadratic. So I'm going to take out the 3 that's the common factor first, which leaves us with t squared minus 4t plus 3. And I can actually divide that 3 out, so I'm not going to worry about it from this point on, but I am going to factor that quadratic. So to get t squared minus 4t plus 3, I need to multiply -1 and -3 to get +3, and that will add up to -4 for your middle term. And when I set each factor equal to 0, I end up with t equals 1 and t equals 3. So my particle comes to rest after 1 second and after 3 seconds. Okay. Now the next part says when is the particle moving forward? That is in the positive direction. When your velocity is positive, your particle is moving to the right, or if we were talking about a vertical situation, your particle would be moving up. If your velocity is negative, your particle moves either left or down, depending if you're working on a horizontal axis or vertical axis. So what we need to do is set up something similar to our sign chart that we do when we're finding maxes and mins. So we're going to look at velocity and position, starting from time 0. Okay, then our particle stopped at time 1 and time 3, and right now we don't have an ending time, so I'm just going to leave that open-ended for right now, or you can say infinity, even though the particle's not going to keep moving forever. Okay, so we need to test this, and remember our velocity equation was 3 times t minus 1 times t minus 3. I'm going to use the factored form because it's easier. The 3 again is not really going to affect our answer because we're only looking to see is velocity positive or negative. So I need to choose a number that is between 0 and 1 for a test point. So for the first interval, I'm going to test it with t equals a half. So I only need to think about is 1/2 minus 1 positive or negative, and 1/2 minus 3, same thing. So I get a negative times a negative, which gives me a positive. And if my velocity is positive, my particle is moving forward or to the right. Okay, now for the next two intervals, we actually have some values we've already tested. Okay, when t was 2, if you look back at part B, we came out with -3. So our velocity was negative, which means the particle is moving backward or to the left. And beyond the 3, we already tested v of 4, and we got v of 4 was +9, so it's positive, and again moving forward. So this particle is moving forward or in the positive direction from 0 seconds to 1 second, and from when t is greater than 3. Or you could write that as 3 to infinity. Okay, so we have two intervals when our particle is moving forward. From time 1 to time 3, our particle is moving backward or to the left. Okay, now part E we are actually going to work on as we do part F and part G, because we're going to need some of the numbers we're going to find before we can actually sketch this graph to draw a diagram that represents the motion. Okay, so to find the displacement of the particle during the first 5 seconds, remember we said that displacement was the difference between your starting position and your ending position. And if I want the first 5 seconds, I'm starting at time 0 and I'm ending at time 5. So I need to find my position at 0 and my position at 5. And notice this is position, it is not the velocity equation. So I'm going to take my original equation, the t cubed minus 6t squared plus 9t, and I'm going to plug in 0 and 5. And when you plug in 0, you're just going to end up with 0. So my particle starts at position 0 meters. Plug in the 5. And when you plug in the 5, you will end up with an answer of 20 meters. So my displacement would be the difference between my starting and my ending point. So S of 5 minus S of 0, or 20 minus 0, is going to be 20 meters. So my particle is 20 meters from where it started at the very end. Okay, now remember, difference between total distance and displacement. If my particle had been moving forward the whole time, then my total distance would also be 20. But it didn't. It was moving backward from time 1 to time 3. So we also need to know what its position was at those times when it stopped or came to rest. So we're going to have to figure out S of 1 and S of 3, again by plugging in your numbers. And I'd like you to pause the video and try this on your own, and then start the video again when you get the position at time 1 and the position at time 3. The position at time 1 should have equaled 4 meters, and the position at time 3 should have been back to 0 meters. Okay, so now let's draw our diagram and then we will figure out our total distance. Okay, so on this number line, I'm starting from 0, and I'm going to have to, remember we're ending at 20, so we're going to be counting by 2's. Okay, so from time 0 to time 1, I am moving forward, and I end up at 4. So I've moved 4 meters in the first second. From time 1 to time 3, I ended up back at 0. So I went backwards another 4 meters. Okay, and then at time 20, or at time 5, I went to 20 meters, so that's a distance of 20. So I have traveled, my total distance is going to be the 4 meters I went in the first second to get from 0 to 4, plus the 4 meters I went from the first second to the third second that got me back to 0, and then the 20 meters from time 3 to 5 that I traveled, and so my total distance is 28 meters. Remember, total distance takes into account all the back and forth. Okay, the next thing we're going to talk about then is acceleration. So acceleration, keep in mind, is the derivative of velocity. And our velocity equation was 3t squared minus 12t plus 9. So to find the acceleration, we're going to have to take the derivative. Derivative of 3t squared is 6t. Derivative of 12t is 12, and the derivative of 9 is 0. Okay, so to find the acceleration after 4 seconds, now we're going to just plug in the 4 to our acceleration equation. So 6 times 4 minus 12 would give you 12 for an answer, and the units on this will be meters per second, or meters per second squared, because acceleration is the rate of change of velocity with respect to time, and the rate of change of the velocity was the meters per second, and then the time is still seconds. So acceleration is meters per second squared. Okay, now for the last two questions, last two examples. Graph the position, velocity, and acceleration functions. Okay, so I used a calculator. The window is shown here, and this is the graph that you end up with, but let's label which graph goes with position, acceleration, and velocity. Okay, so our position, remember, was a cubic function, so it is the graph that is going up and down. Okay, this is S of t. Our velocity was a quadratic function, 3t squared, and so on. So that is the parabola. And our acceleration function is a line. It was a linear equation, 6t minus 12. Okay, so here is your graph. And again, I just used the calculator to get this. And notice it said we were only looking from t equals 0 to t equals 5, which is why your x min and x max are 0 and 5. Okay, part J then talks about when is the particle speeding up and when is it slowing down. So what you need to know is that your particle is speeding up when your velocity and acceleration have the same signs. So both positive or both negative. Both above the axis or both below the axis. Your particle will be slowing down when velocity and acceleration are different signs. So one is above the axis and one is below. Okay, so instead of trying to do this from the graph that's showing on this screen, I have hidden the graph of S of t, the position graph, because for speeding up and slowing down, we only need to look at the graph of velocity and acceleration. And anywhere that those graphs cross the axis is a place where one either velocity or acceleration changes. So at time 1, time 2, and time 3, one of those graphs will hit the axis. So we've got something going on from time 0 to 1. Okay, we've got something else happening from 1 to 2, and then from 2 to 3, and from 3 to 5. So we need to see in these intervals, are velocity and acceleration the same or are they different? Okay, so I'm going to draw a line all the way through this graph so it'll be easier to determine. Okay, so if you look at the first interval from 0 to 1, my velocity graph is above the x-axis and my acceleration graph is below the x-axis. So velocity is positive and my acceleration is negative. If they are opposite signs, then the particle is slowing down. Okay. From 1 to 2, however, they're both below the axis. So both velocity and acceleration are negative. Okay, and if they're both negative, they're the same sign, then your particle is speeding up. Okay, from 2 to 3, we've got acceleration above the axis, that's positive, and velocity is below the axis, so that's negative. So opposite signs means your particle is slowing down. And then from 3 on, both of these functions are above the axis, so they're both positive. And when your velocity and acceleration are the same sign, then your particle is speeding up. Okay, now this is the end of these notes, but please go back, and if there was anything that you were still confused on, put a question mark beside it and ask me in class when we start discussing particle motion.